some of the flushing experiments that we've seen. This is the situation we had. This is the bed pack model that I showed you in a previous lecture, the one that we had Juliana's experiment, and how it was recorded. Her recording sections were done in the same situation. Okay? So, as you see here, we have our ternary diagram, and what I'm showing you is some ideas of density and how it works in the field, as you've seen. Look, as we have ethanol injected, I was injecting ethanol from top, so like we've seen in Juliana's experiment. Ethanol mixes with a little bit of aqueous phase, right? That was in the field. You've seen that? You had first the gasoline residuals, and then it reaches and mixes with the water phase. As it mixes with the water phase, it tends to go, you see this B, which is the aqueous phase, and this is ethanol with gasoline. So you have the oleic phase or gasoline phase as we call it. Well, the density of B is higher than the density of C. And what happens is that by density, it goes down and it develops a finger, right? Aqueous phase is always density because it's here. So that's what I showed you. The density is higher and it goes down and it stops here at the top of the water table. Look. Well, should we add ethanol from the bottom? Let's say I'm cleaning my residual phase, and instead of adding ethanol at the top, I inject ethanol at the bottom, underneath the water table. Well, ethanol is less dense, it's going to go up, and gasoline is less dense as well. So ethanol tends to flush it and get all the gasoline out. That was probably a clever idea. It's much better than going ethanol from the top as an injection, as a flushing strategy. Well, let's take a look at that. When we inject ethanol here, it mixes with aqueous phase B, right? Well, density here of this point A, pure ethanol. Well, density is lower than B, right? If A is lower than B, it goes through here, right, to the oleic phase, right? And that's the aqueous phase D, right? Sometimes it is mixing. So I'm injecting underneath and it reaches that. What happens is we still have the local instability here, right? This phase C and the aqueous phase that we'll have there, it's heavier and it goes down. So it develops finger as well. Okay? So what I'm seeing, we decided is let's try a lateral flush as we actually have done in the field. This is a very big, this is 35 centimeter, this big glass bead mold. This is because we cracked the mold. It didn't crack, no problems with the porous medium itself. It's just the cover that was cracked. So we add a bit of a glue here so we could keep the experiment going. And we will see what happens. Take a look. As we injected ethanol from, it develops some fingers here. Look. Residuals being reprecipitated at the front of the ethanol flushing. You see, as you move that, you have some water phase that has more mobility, and you have the part of gasoline, because you remember you have a gasoline phase and a water phase that has all the three parts. That one that is richer in gasoline reprecipitates as ethanol moves on. But more ethanol is coming behind, and it's moving those guys ahead. Look at that. Look at that. It's not a movie, some still that I try to mimic as a movie. But look at that, how the ethanol flushes. we see that we clearly have a big finger here. More ethanol coming here and more ethanol coming here. Not all the points travel at the same speed. Look, a finger here, a finger there, and then it kept cleaning. Once more, so you can see. Apparently that worked very well, right? So we have the gasoline residues being flushed by ethanol and cleaning up the whole thing. That was great. Okay, so we moved to the field with that. On the field scale we had some representation. We used TDR, time domain reflectometry, to measure saturation, and we also used the neutron probe. So this is the how we measure, right? Take a look at that. This was a 2x2 cell, right? We have a 12% average residual saturation. This is the water table, and we have a zone of residuals. This is before, and then after we inject. Look, this is saturation, and now it's after we injected the residuals. You see the big difference that we measure with TDR against neutron probe. So we can see that we did develop a big residual zone here. That worked from our geophysics. We're not using other measurements, just geophysics. Well, what we've done then, we had 13 injecting points here, and 14 and 14 extraction points here. We injected ethanol here and tried to flush. Okay. Well, what happens next is that what we see, look, was from right to left, the flushing, right to left. Well, one thing that we realized, and when you go to the field, you do learn what happens in the real life. Well, we had that nice experiment that I showed you in the lab, but at that experiment, since our groundwater velocity was much higher, although lower than the capillary number that we mentioned, in the field that velocity is much lower, and then density differences are major for influencing the field, and our ethanol moved straight up. See, straight up, and it tended to pool on top of our residual phase. So what I've done, first we injected ethanol without much pumping, and then we pumped so we could lower the front of ethanol, and ethanol could reach the residual phase. And we actually have seen the residuals moving. That's how we were cleaning up. See, this is clean. And these were sampled. We have all the sampling points here, these dots are sampling points. And we were also measuring the development using neutron probe and TDR. Okay, look at that. That's the cleaning, that's the cleaning, right? That's the last that we have after pumping. Look at that. Ethanol was developing, and we're actually injecting more ethanol to have higher concentration here. And this is after pumping. This is a pumping zone, and you see how it cleaned. That's concentration of ethanol. Okay? Gasoline residuals. That's when we started flushing and look at the development of the gasoline residue. And even after we finished the experiment, we ended up having lots of gasoline content, right? Why? Because we couldn't clean that with ethanol due to density difference. The cleaning was much better at the top, but as the mixing is also less dense, you tend to have some concentrations here at the top. More ethanol concentrations at the top. Well, when you do flushing, what matters most as you're flushing of choice has density difference is the density difference, right? That's all we have. Look, comparing both. So, okay. And that's all we have, all right? So, as I mentioned to you, when you have we were focusing on the two-phase and multiple phase part of the experiment, and we forgot about density differences. Well, today that we have a lot of discussion about how presenting bad results in science is not being well received by scientists. Well, you should present your bad results, although not very good like mine. You understand from not doing correct things. When you do mistakes, you learn as well. Actually, we learn from our mistakes. And we learn from some other people's mistakes as well. Okay? Thank you very much, and I hope you enjoyed this video lecture.